Our group did an optimization for the e-bike. This slide gives the system-level overview of our model. We split the problem into three subsystems: frame, energy storage, and drivetrain. The frame subsystem optimizes the tubing to minimize frame mass while satisfying structural and geometric constraints. The ESS subsystem selects battery configuration and cell type to maximize stored energy while meeting packaging and electrical requirements. The drivetrain subsystem selects the motor and operating point to minimize energy consumption per mile under torque, power, and acceleration constraints. These subsystems are all connected to shared mass, power, voltage, and packaging variables. In the last step, the whole optimization is solved together to maximize the range of the e-bike.
This slide introduces our team's overall optimization model for the e-bike system and lays out the key parameters and intermediate variables for each subsystem. On the left, we define the frame subsystem. Two blanks, material properties like aluminum density, yield strength, and Young's modulus, which drive stiffness, stress, and buckling behavior. In the center, we summarize the battery and energy storage system, including the cell data table, pack geometry limits, maximum battery mass, and the casing factors that scale mass and dimensions. On the right is the drivetrain subsystem, including wheel radius, drivetrain efficiency, cruise speed, accelerations per mile, and the motor and vehicle parameters that determine forces, power, and energy use. The lower half of the slide shows the corresponding intermediate variables. Quantities like frame mass, battery mass, and geometry, and drivetrain energy per mile that link these inputs to system performance and ultimately feed into the optimization objective. This slide pulls the pieces together into the formal optimization problem and highlights the main design trade-offs our team is exploring. On the left, we define the design variables: frame geometry through tube outer diameters and thicknesses, ESS design through the number of cells in series and parallel in the chosen cell type, and drivetrain design through the selected motor option and commanded launch acceleration. The middle column shows the side constraints, including the bounds on frame tube dimensions, battery mass and package size, and drivetrain limits. On the right, we state the system-level objective function. We maximize range per unit energy consumption over both integer and continuous decision variables. The lower part of the slide summarizes the key constraints and trade-offs. Lighter frame tubes reduce mass but push stresses toward yield. More cells increase capacity but add battery mass. And a larger motor improves torque and acceleration at the expense of added mass and reduced range. These relationships define the feasible design space that our team's optimization explores.
For the mathematical modeling, these are the assumptions and steps for each subsystem. For the frame, the main design variables were tube diameters and thicknesses, so we used an analytical model to evaluate combined axial and bending stresses under a 3G vertical impact with rider's mass. This optimization dictates the maximum allowable dimensions for the battery pack. For the ESS, we used an analytical battery pack sizing model with integer variables for the number of cells in series and parallel, along with discrete cell selection from a commercial database. Using the selected cell properties, we computed pack voltage, power, mass, and dimensions. For the drivetrain, we used an analytical point mass longitudinal vehicle model with discrete motor selection. By calculating aerodynamic drag, rolling resistance, and electrical resist during launch, we formulate the energy consumption per mile to select the optimal motor option. Consequently, all three subsystems are tightly coupled and globally optimized using a genetic algorithm called GA.
A genetic algorithm was selected to solve our e-bike's IDF system optimization model. The primary rationale behind choosing a genetic algorithm was our use of two different sources of discrete data, lookup tables for both our motor and cell selection. MATLAB was our software of choice for this optimization, as all subsystem optimization up until this point had already been conducted in MATLAB, so integrating these models into a system-level model was more straightforward. Due to the complex nature of our subsystem analysis functions, we pursued two different schemes in order to reduce model runtime. Prior to starting our genetic algorithm, we initialized our lookup tables by reading them into MATLAB at the beginning, so this wouldn't be done every iteration. Additionally, with the support of MATLAB's parallel computing toolbox, we were able to run the genetic algorithm using multi-core processing, which significantly improved runtime. Due to the nature of the heuristic genetic algorithm we chose for this system optimization, we've observed quite a bit of variation in our f-star value. For this reason, we decided to run 10 iterations so we can capture some of this variation in a table. After 10 iterations, our models achieved an optimal e-bike range or f-star value of 67 miles. The box plot on the bottom left of the screen illustrates this run-to-run variation, which is expected for this type of algorithm. The table on the left of the screen shows the design variables that correspond with our optimal f-star value of 67 miles. We believe these values are reasonable given the constraints and the design objective of this e-bike, and we'll discuss this further in a few slides. Both the heat map and the box plot of the constraint activity is shown on the right-hand side of this slide. It appears that the constraints of the most variation are the frame buckling constraints, which we expect as this requirement is likely more stringent than required, but was included for thorough structural development of the frame.
Shown here is the parameter sensitivity analysis results, ordered from highest to lowest sensitivity based on a normalized sensitivity coefficient. The most sensitive parameter is the case mass increase factor, which accounts for extra mass of the battery case and wiring. Based on the standard sensitivity coefficient alone, it appears that the rolling resistance coefficient CRR is the most sensitive parameter, but it also has the smallest parameter values. Likewise, the sensitivity for Young's modulus E appears to be the smallest at 0, but it also has the largest parameter values. Normalization of the sensitivity coefficient was necessary to compare how changes of parameters of different units affects the resulting objective function for range. Based on this, we can say that a 24% increase in the alpha case parameter results in a 30% decrease of the e-bike range. Therefore, we can directly compare the normalized coefficient between parameters. Note that alpha case, beta case, and E parameters have limitations to what values could be analyzed.
Moving into our constraint sensitivity analysis, we evaluated all of our constraints, side constraints, linear and nonlinear equality and inequality constraints. However, listed here, we see the effects of our active constraints on our optimization model. What we have here is that the outer diameter limits on tube 1 of our frame subsystem ended up having the highest sensitivity coefficient, meaning as we loosened the lower bound on this limit, we had a significant difference in the e-bike range in comparison to our optimal range that we received in our optimal X star. We could also see the significant effects of the launch acceleration and the thickness of 2 of the other tubes in our frame subsystem as well. And then in our nonlinear inequality constraints, the nominal voltage of the battery and motor limits also resulted in a difference in our F star. What's important to note here is that we are using GA for our optimization, and so the results of our constraint sensitivity analysis are also subject to the inherent variability of using a heuristic algorithm, not just these perturbations that we're introducing.
To validate our optimized solution, we compared the ranges of other similar competitor e-bike models. Based on different sources for other competitor e-bikes, standard range calculations were often calculated differently. Therefore, a normalized range estimate was derived using the battery capacity of the other e-bikes. A new e-consume estimated is calculated with the mass of the rider, the mass of the frame estimated, where that equals the mass of the e-bike minus 10 kilograms, and the X star, X 16, 17, and 18, from the optimal F star value. Note that 10 kilograms is the average mass of 2 wheels plus the motor system in e-bikes. Using the system objective function, the estimated range values for the competitor e-bikes are populated in the table below. The designed system e-bike compared to the 4 separate other commercial options proved to have the most optimized range, normalized based off of the new e-consume estimated. At the interim optimizations of the subsystem level, the cruising range was optimized to be only 42 miles. After linking the 3 subsystems together with systems modeling, the optimal cruising range ended up being 67 miles. The systems model shows a 59.99% increase in the total range of the e-bike when each of the subsystems are optimized together. The bottom table shows the results of each of the subsystem optimizations along with the system optimizations. The table on the right shows the corresponding X-star values at a subsystem and system level. The significant increase in performance was mainly due to key decisions made in the system's modeling. Mounting the battery pack below tube 3 on the frame subsystem allowed for Lmax constraint to increase, allowing for the number of cells in series to increase. Since row 4 of the motor table was chosen, the nominal voltage increased to 60 volts instead of 48 volts in the subsystem level of optimization. This allowed for more battery cells to be added into the energy storage system. 5 more cells were able to be arranged in each row, resulting in a much higher energy capacity.
Due to the heuristic nature of the GA algorithm, we required multiple runs to catch the true optimal F star, and our sensitivity analyses were less accurate. We could improve this by switching to a fmin-con based algorithm, but we would need to relax our integer design variables for cell stacking and run more iterations of the algorithm to cover each combination of rows in the cell and motor selection matrices. From there, we could wrap in a branch and bound algorithm to find the closest feasible integer solutions. Additionally, there was a consistent gap of 70 millimeters for our battery width, but the active constraint blocking additional cells was voltage, not packaging space. So if we separated our wiring variables from our stacking variables, we could potentially add capacity, resulting in more range. However, since this would add more integer variables, we would need to iterate the fmin-con function even more times to identify the true optimal solution using these workarounds.